In this example, we will use the Aerospace Toolbox and block set to perform a Hohmann transfer of a spacecraft between two circular coplanar orbits. By the end of this video, you will learn how to perform key aspects of a Hohmann transfer, including calculating the required delta V, the correct time and duration of the maneuver, and the attitude requirements at each maneuver. Hohmann transfers are generally the most energy-efficient maneuver to get from a current orbit to a desired orbit in the same plane. It is useful in cases where time of flight is not a significant concern, but minimizing the amount of propellant used is. This image illustrates the different parts of the Hohmann transfer, where the red innermost circle indicates the initial orbit, the magenta ellipse the transfer orbit, with the dashed section showing what the remainder of the orbit would have looked like if we did not perform the second maneuver, and the green outermost circle indicating what the final orbit would look like. We can also see delta V1 and delta V2 here, indicating where the maneuvers are performed. First, we need to define the mission and the mission objectives. This includes the mission time frame, the initial orbit parameters, and the orbit parameters of the final orbit. In this example, we would like to raise the orbit of a circular orbit with a semi-major axis of 7,000 kilometers up to 10,000 kilometers. The timeline of the mission will be as follows. Complete one full orbit at the lower altitude. Perform the first maneuver to enter the transfer orbit. Perform the second maneuver upon reaching apogee of the transfer orbit. And then complete one orbit at the higher altitude. With the mission defined, we can begin computing the transfer times and required maneuvers. We first start by computing the orbital period of each orbit to determine when each maneuver needs to be performed and when the scenario needs to end. The period of an orbit can be computed as a function of the semi-major axes of the spacecraft's orbit and the standard gravitational parameter of the central body. With the time of burn computed, we need more information on the application of the delta V, specifically its magnitude and direction. We can use the following equation to compute the delta V required at each of the maneuver times determined earlier. With the maneuver time and the required delta V calculated, we now need to compute the direction the delta V needs to be applied in using the following equation. Now that we have the specifications of the maneuver and the time and the mission they are to be performed at, we can begin computing the burn duration required to obtain the given delta V. To do this, we will assign the following thrust parameters to the thrusters on the satellite. It is important to note that while we are treating the thrust maneuver as non-instantaneous, we use relatively large thrust parameters here to approximate the burn as nearly impulsive. We can compute the final mass after each maneuver by using the rocket equation and using the differences between the initial and final mass along with the given flow rate to compute the required burn time. This is repeated for the second maneuver, this time using the final mass of the first maneuver as the initial mass of the second maneuver. We now have all the values necessary to simulate the model and obtain position and attitude history. Open the Hohmann transfer model. The model has three parts: the maneuver section, the spacecraft section, and the attitude controller section. The maneuver subsystem is responsible for generating the burn command when the current time reaches the burn time computed earlier and lasts for the duration of the burn we also computed. It also returns the burn direction computed earlier so that the delta V is applied in the correct direction. The spacecraft subsystem models the motion in the form of satellite position and attitude history using the spacecraft dynamics block, given the body moments, mass flow rate, and the exhaust velocity as inputs. Finally, the attitude controller subsystem calculates the body moments needed to align the spacecraft with the direction the burn is to be performed in. Run the model to generate the position and attitude history. Now that we have the position and attitude time history, we can use the time series to timetable function to extract the data into a timetable format. The next step is to create a satellite scenario and add the satellite with the given position and attitude histories. Use the point at and coordinate axes commands to view the orientation of the satellite throughout the simulation. Launch and play the scenario to visualize the Hohmann transfer from start to finish. As we can see here, the satellite first starts by completing a full orbit at the lower altitude. It then points in the maneuver direction and raises the orbit to enter the transfer orbit, completes half the transfer orbit, points in the second maneuver direction computed, and performs the last maneuver to complete the Hohmann transfer. To learn more about how to use the Satellite Scenario Viewer, see the Introduction to Orbit Propagation and Visualization video for an in-depth overview. This includes a more in-depth guide on using the Satellite Scenario Viewer, which can be found in the Aerospace Toolbox. To view the derivations in more detail and to try the example covered in this video yourself, see the Hohmann transfer with Spacecraft Dynamics block documentation. You can find the links to both documentation pages in the video description.